Guys, welcome to another episode of Tradecraft Tuesday. We're here every Tuesday exposing hacker tradecraft, and this week we're kind of hitting an episode close to our hearts, which is fuzzing for vulnerabilities, talking about why hackers, security researchers, or software developers do it, what you can get out of it. Just to recap, we're here roughly every Tuesday at noon. You can find us on Cyber, you can find us on YouTube. You could also live chat with us in our Slack channel. We tweeted it just a little bit ago on how to get an invite into that Slack channel. Just real quick before we dive into the news like we do in every episode, want to give a reminder, next week we are going to be off. Chris and I are instructing, ironically, a Fuzzing for Vulnerabilities class at Black Hat and are not going to be able to stop class, sadly, to live stream a video. But with that said, please send us your comments, questions, and suggestions about what to do in future episodes. All right, Chris, now that we took care of the introduction, let's talk about some news this week, man. I already said, Black Hat and DEF CON's going this week. It's going to be exciting. I think there's a lot of good talks.
Yep. Yeah, definitely when we come back from Black Hat, we'll probably have to do an episode or maybe even two just on some of the talks that were there and, how that affects people and stuff. So I guess stay tuned for that.
Yeah, also, some of our followers on Tradecraft Tuesday suggested, hey, since we're not doing an episode, let's get together for a dinner or something along those lines. So we're going to be crashing a dinner invitation that Movix put out saying, hey, we're getting together on Thursday night at Texas Day Brazil in Vegas. We'll post stuff from our Twitter page on where you can join us there as well. It sounds like that's going to be the official get-together while we're out there in Vegas.
Yeah, definitely. Come hang out. It'd be cool to meet some of the people who watch the show and, get some feedback or whatever.
So moving on, we had, ironically, a lot of the folks who've been here on Tradecraft Tuesday in the past have actually put some really great research out this week. And I thought this was a great segment to maybe point out some of that research. Since we talk about news, one of those was a really neat blog put out by Matt Nelson. I think Matt Graber participated in some of this research, but it was on bypassing UAC in Windows 10 using the disk cleanup. I won't go too in-depth in it since this is not the episode, but essentially it's using some DLL hijacking to abuse a race condition that's caused by an auto-elevating scheduled task, and it natively ships on Windows 10. So if you guys haven't seen it, jump on over to Matt's blog at enigmaox3.net.
We'll post the link in the show notes.
I'd say furthermore, we also had Matt Graber lived up to his name with his blog Exploit Monday by dropping a privilege escalation for Windows 10 IoT core build. I think it was 14.393, but don't quote me on that. Anyway, they found a misconfigured service ACL that led to privilege escalation. So very cool. Check that out on Exploit Monday. Also in news this week, Symantec. We had talked about the patchwork APT before, but Symantec included actually some really neat additional tradecraft in regards to that APT that Kaspersky and Cymeria, I think was their name, had also detailed earlier this week. Some neat exploits, backdoors, and targeted industries that weren't covered before.
Yeah.
So that wraps up news, Chris.
Cool.
Let's do this, man. Fuzzing, we know this like the back of our hand when it comes down to it. So why don't you start me out? What the heck is fuzzing for somebody who doesn't know?
Yeah, all right. So fuzzing, for anybody who hasn't heard about this, it's not real popular actually outside of really the security community, but within the security community, it's pretty well known. But so basically, fuzzing is a brute force method for finding vulnerabilities in software. So as an attacker, you could sit down with either a binary or with some source, and you could spend a lot of time auditing it, trying to figure out how it works, what all the pieces do to try to find a vulnerability. But one of the other really common methods, and something that's been around for a long time, is just setting it up to try and brute force finding a vulnerability. So the basic approach is you're going to take some target application. For this, let's just go ahead and say it's Adobe Reader, just to make this simple. So you're going to take Adobe Reader, and you are going to run Adobe Reader hundreds of thousands, if not millions of times. And what you're going to do is every time you start it, you're going to tell it to open a PDF. And before you give it the PDF to open, you're going to take that PDF and you're going to corrupt it in some fashion. And that way you can try to see when Adobe Reader tries to open this PDF, oops, it crashed. Okay, so that's really what attackers are looking for, is how can we provide a bunch of inputs in some automated fashion and cause crashes in like Adobe Reader or Internet Explorer or Chrome or really any other software that's going to parse untrusted user input.
So Chris, I'm gonna play the naive devil's advocate here. You said input, and right away I've heard of this buffer overflow vulnerabilities. You know, it sounds like you give input and it causes it to do something. Is that something that you could find from fuzzing?
Yeah, I mean, definitely. I mean, you're fuzzing, you'll find a lot of bugs. You know, buffer overflows on the stack and on the heap. You'll find like use after freeze, all kinds of stuff. Really, fuzzing is only limited to like the time that you put in. Not all bugs are as easy to find, right? It's really easy to detect when a program has crashed. It's not as easy to detect some of the more subtle like logic vulnerabilities. Like say I provide some input to an application and that causes it to try and load a DLL with a specific name, right? And maybe that name came from some input that I provided. That's not as easy to detect because the program doesn't crash. It just fails to load a DLL and moves on. Some of the other things that are hard to detect are like command injection, because again, you might provide some input that it then tries to execute as a command, and then it basically just finds like, oh, that program doesn't exist, whatever, we're going to move on. So like take, for example, like maybe 2 weeks ago, there was a bug in ImageMagick where when processing some images, you could basically specify some stuff and ImageMagick would try to execute a program. And if you basically crafted a malicious image, you could get it to run things like wget and download and execute files and all kinds of terrible stuff. So something like that is hard to find with fuzzing just because of the instrumentation you have to go through. Because really the key thing with fuzzing is trying to tell it how to detect when some behavior happens. So it's easy to, like I said, it's easy to detect and specify the behavior of the program crashing.
Gotcha. So you gave the Adobe Reader example. You know, Adobe Reader reads in files, PDF files as input, but it doesn't always have to be files. What about like network protocols and stuff like that? Is that something you could fuzz as well?
Yeah. I mean, you can. It's really kind of any input that you can give. So, like you said, you could be from a network protocol, right? You could fuzz an HTTP service, like Apache or Nginx or something like that. You can fuzz those. You can fuzz web applications, right? Like if maybe they have a bunch of fields that they accept through the URL or through JSON or whatever. You can throw a bunch of stuff in there and see what it happens. Burp Suite has some limited functionality for doing some fuzzing of web applications. So it doesn't have to be a file. A file is usually the example I start with because it's easiest for beginners to conceptualize. Okay, I took a file, I changed it in some way, I now have this other file which is corrupted.
Gotcha, man. So how do I get started, right? You just gave me a heads up. You told me you're going to do all kinds of changes, whether it's to files or whatever the input is. Yep. And the idea behind it is you're setting up some instrumentation to find out when something that's not expected happens. So what do I do? How does an attacker or a software developer or anybody get involved in fuzzing?
Yeah, so the easiest way to get involved in fuzzing is to use one of these already existing like fuzzing frameworks. So probably the most popular one, which came out like maybe like 2 years ago, 3 years ago, is AFL, American Fuzzy Lop. It's a program created by a guy named Michael Zalewski. He works for Google, and kind of what set it apart from a lot of other fuzzers is really like this novel technique that he created so that the fuzzer could know when it was reaching new code. And code that you've never reached before is now interesting code because that's something new that you can fuzz. So you could download AFL. It's really easy to get started. I mean, it takes you about 5 minutes. Like say you had a program you wanted to fuzz. You basically compile AFL, you compile the program with AFL, then you start AFL, right? It's very simple. Some of the downsides are it's only Linux. It has limited support on OS X. Almost no support on Windows, although recently, maybe like, what was it, like last week, I think somebody came out with some stuff to kind of help on Windows. WinAFL, I believe, is what the project is called.
Yeah, that was Ivan Frantic that released on GitHub, WinAFL.
Okay, yeah, so it's a little bit better, but it's still really slow. Windows doesn't have some of the built-in features that Linux has. So Linux does something called forking, where a process can basically clone itself and then run. And it's a very common thing to do on Linux, where instead of like having traditional threads, most programs will just fork a clone of themselves, and then both the original and the clone can run. And they share the memory that existed before until one of them writes to it, and then they get two separate copies. So that's what makes it fast on Linux. Windows doesn't have any kind of forking feature, and some people have tried to like make one. Richard Johnson of Cisco Talos, they had done some work to try and make a fast fork on Windows. I talked to him like last week. He said that it worked, but they've had to sideline a lot of the stuff because just other things have come up. So mostly AFL is used on Linux. If you want to do something on Windows, you have some other options, like Sully is a popular one. So Sully is a fuzzing framework written in Python. It was originally created by Pedram Amini and Aaron Portnoy and some other guys from ZDI. I've used it a bunch. It's pretty good. Peach Fuzz. So Peach Fuzz used to be pretty popular. It lost a lot of popularity when they took it private. So there's still the Peach Fuzz community version and open source version, but they refactored a lot of the stuff and made it a commercial product. I've never tried that, so I can't speak to how well that works. But there's a lot of like fuzzing frameworks you can get, and the easiest way to start is to go download one of these and just start fuzzing something.
Gotcha. So jumping back to our example, because it just seemed really easy to kind of follow the Adobe Reader example for the show. Say I've got AFL, or I've got Peach and Sully. They're doing complex things under the hood. And you and I both know from our experience that there's different techniques to fuzz different files, how to make modifications, whether they're files that already exist. One of those is mutational fuzzing. And we use this, Chris, a whole lot in our class to really show that how you can take existing files, which are valid input files. These are valid PDFs, for instance, that have different functionality, and then how we can mutate them in kind of a deterministic or even a random fashion to be able to make subtle changes to these files. Why is that so successful? When it comes down to finding
really, it's just about being simple. It doesn't take a lot of effort, right? Like if I go to Google, I can download tons of PDFs. Like I can find lots of archives of PDFs, zip files of PDFs. So within a couple hours, I can probably have 100 different PDFs, and it's very simple to just take a file, copy it, modify some bytes randomly, and start Adobe Reader passing in that file. Like it's very easy. I can start a fuzzing like that in probably 10 or 15 minutes. And it's also very fast because there's not a lot of computation I got to do. I can start up 20 instances of Adobe Reader at any given time and let them run. So Mutational, for that reason, is popular because it's easy to get started. There's some other techniques that are a little bit less popular, but could potentially give different results. And the problem with fuzzing is it's not really a science. It's more of an art. So there's no I can't give you the steps and say, okay, if you do step 1, 2, and 3, you will find bugs, right? There's just kind of a bunch of different techniques that you can apply to try and find bugs in different fashions. Mutational fuzzing is one of them. Another technique is generational fuzzing. So whereas with mutational, you started with valid files and you tried to corrupt them somehow, with generational fuzzing, you're going to start with the protocol, the file specification. So you'd go and you would find okay, what does a PDF file consist of? Okay, it consists of this header, and this header has these fields, and the fields are this type, and they contain this type of data. And you would write a script that would literally go through and say, okay, well, we need an integer, so let's insert an integer here, and we need a string, and let's put a string here, and we need some data here. Okay, this is an image, and you would build a PDF file from nothing. And so not a lot of people get to this point because it's kind of a lot of work. I mean, if there's no specification, you're looking at doing a lot of reverse engineering to figure out, like, what does the file need to consist of? It's a lot of work to build complex files. I mean, you could build a simple PDF file with like some text, but then again, because it's a simple file, what's the chance that Adobe Reader is going to crash on that, right? So there's kind of a lot of work behind generational fuzzing, but the potential for hitting other bugs that you couldn't hit with mutational fuzzing is there. So there's kind of a time, trade-off there that you gotta figure out if you're willing to put in the time.
And I just want to touch on real quick, we've talked about two of those techniques, mutational and generational fuzzing. The reason that these bugs exist is the file formats in this example are extremely complicated. Chris was alluding to that, hey, you might not get many results with simple file formats or PDF files, for instance, in this example, that don't have a lot of functionality. But if you think about it, on the other end, there's a developer that is at Adobe implementing the PDF spec, and it's really easy to introduce a bad instruction or poor logic, or a case where you think you're bailing out of something successfully, but you happen to not, or you don't, maybe you free something that's later used, or you accidentally write something that was unexpected to be written in a certain location. So what we're really talking about here is the downfall of just software development, period, at this moment. It's software development is complex. Handling complex anything, whether it's streaming audio, protocols for the network, authentication, rendering of movies, rendering of PDFs. I mean, if you think about it, PDFs have JavaScript support inside there. You can embed all kinds of different media, whether pictures.
You can build custom forms that do different things. There's all kinds of stuff you can put in there. I mean, like, look at here's a good example that's had like thousands of bugs. Flash, right? Look what Flash does. It renders images, it renders videos. You can put all kinds of executable code in the form of action script behind it to do all sorts of different things. You can interact with the browser. There's a lot of surface area there, and so. If you're looking for something to fuzz to find vulnerabilities, what you want to look for is something with a lot of attack surface, something like a Flash, something like Adobe Reader, a browser. I mean, if you look at it from the perspective of an attacker, a browser is basically an application that downloads and executes untrusted content from the internet, right? I mean, already there, huge attack surface. On the opposite end, something that doesn't have a lot of attack surface would be something like, I don't know, maybe like Notepad, right? What does Notepad do? Well, it opens a file and it displays text, right? It's not really parsing much. It's just taking the characters that were in the file and putting them now onto a graphical user interface. So there's not a lot of attack surface there. So you could mutate the file all day. Highly unlikely you're going to find a bug in something like Notepad. Yeah,
what is it? It handles a couple byte order markups for a couple UTF and Unicode formats.
Right.
Unlikely for a bug to happen there. Anyways, we digress, but hopefully the point we've got across here is developing software is hard. Fuzzing is a great way, whether you're using it as a hacker, to find vulnerabilities that potentially could be exploitable or bugs that could be exploitable. It's also a very complementary tool to develop better software. Chris said earlier, while you're writing code or while you're performing a code review, you could have your mutational fuzzer, which is really easy to put together, running. And I think that's a great tip for anybody who writes software. In class, we joke, always be fuzzing. And I think it kind of reiterates that point of how a fuzzer could complement what you're doing, even if you're not using it as a hacker would.
Right. Yeah, I mean, there's a lot of development shops who have switched to a sort of a continuous integration type workflow where they have something like a Jenkins server, that every time somebody makes some changes and pushes them to the repository, the Jenkins server will check it out, run a bunch of tests against it, and report back to you as whether or not these tests failed. Well, as part of that, you could also spawn off another task which just said, okay, well, here's the newest thing. Let's fuzz some inputs and have it run them, right? So you get instant feedback, really, like, oh, I committed something yesterday. I came in, the fuzzer had 10 crashes. Uh-oh, what happened, right? You can go back and fix it. In my opinion, if you're a development shop and you're releasing applications and you haven't done at least some very basic mutational fuzzing before you release them, you're really doing a disservice to your customers and yourself, because it's inevitable that, you know, you're going to ship something, somebody's going to fuzz it, they're going to find these bugs, and then it's going to come back on you as to like, oh, now you got to patch these bugs, and you get negative PR that you had that, you know, vulnerable application and stuff. So, you know, when it takes you 20 minutes to set it up, there's really no excuse for not doing it.
So Chris, I do want to shift the blame a little bit here. We've been picking on poor Adobe with the Reader, but Dre in our Slack channel just mentioned, like, hey, take a look at this 2016 CVE that was reported at the end of March. Literally talking about poor Foxit Reader. So that's a good example of this heap buffer overflow vulnerability in another PDF reader. So it's not just poor Adobe.
Right. I mean, it's not just Adobe. I mean, people fuzz and find bugs and things every day. Chrome, Internet Explorer, Adobe Reader. Making my training class, I found a couple of zero-day vulnerabilities in VLC. You know, they're everywhere. Anything that's going to process complex input is likely to have bugs.
So let's get this thing back on tracks. We talked about mutational fuzzing. We talked about generational fuzzing. There's whitebox fuzzing.
Yeah, so whitebox fuzzing is pretty new. I mean, it goes by a lot of different names, and there's no really like standardized name for it yet. Some people can call it testing. I've heard a bunch of different terms for it, but basically, it's kind of a new approach to developing new inputs. So basically, the way it works, and this is kind of high level. So like if you're familiar with Sage or something like that, don't shoot me for trying to you know, simplify this. So basically what happens is you're going to start with a valid file. So let's say we had Adobe Reader, we found a PDF off Google, we downloaded it. Okay, great. Now what we're going to do is we're going to run Adobe Reader, but this time we're going to wrap it in a framework called a binary analysis framework. And what that's going to do is that's going to instrument Adobe Reader, and it's going to follow every instruction that it executes. And from there, it's going to build up this really complicated mathematical formula. So for anybody who's never written software, mostly software is a giant flow chart. Like if you've ever seen one of those flow charts where you like start at one point and it's like, if this, go over here, if that, go down here, and then like toward the end there gets to a thing. That's what software is. It's a big flow chart full of a lot of conditionals to say, like, if the version number is 5, if the field says 10, if the length of this string is greater than 20. So what the binary analysis framework is going to do is it's going to extract all of those, and it's going to create a very large mathematical formula to describe the file. And so they're going to basically, at any given point in the application, they can say, well, execution got to this point in the application because the first 4 bytes in the file were the magic value for PDF, and then this value was 10, and this value was whatever. So once we have that mathematical formula, we can ask these very powerful pieces of software called SMT theorem provers to solve this mathematical formula. So one of the popular ones is Z3, but there's also some other popular ones like RR. So you can pass them this really large formula, and they'll say, oh, okay, if the value of X was 10, then this formula holds true. And so what the whitebox fuzzer will then try to do is for any given conditional, it will say, well, you said this was true for 10, but what if the value is not 10? Is it still valid? And as it does that, it can force flow of the program down all kinds of different paths and try to execute more of the program. So one of the main things in fuzzing is trying to execute as much of the functionality as possible. If you're not executing the functionality when you're fuzzing, there's no way you're going to find a bug in it. So you kind of want to touch as many parts of the program as possible, including those like rarely used features of the protocol that like almost no PDFs have, but it is supported by Adobe Reader. Those are the kind of things you want to go for because that's the code that's going to be most neglected and most likely to still contain vulnerabilities.
You know, I hate to use the term smart fuzzing because that's not exactly the same thing. But we talked about that control flow graph. You know, if this, then do that. If it's greater than this, do that. If this is set, make this decision. And if you think about like the mutational fuzzing that we talked about before, you know, it is truly using, you know, powered by the, you know, random to make 1 byte or n byte modifications to the files. And you don't exactly get the elegance of being able to say, I want to reach this code section, which is rarely touched. And if you think about that, like that is smarter fuzzing, because maybe it, you know, 1 in every 100,000 permutations, you get lucky enough that your random fuzzer modifies the right bit to take you down this code path. But using something like an SMT solver or, you know, the proper binary instrumentation to be able to say, all right, I want to meet these 10 conditions, and then only after those 10 conditions, let's try flipping some of the new logic. So it's really neat to be able to have that granular of control of your input.
Right. Yeah, it can tell you some really amazing things like, okay, I want to fuzz this file, but I still want to reach this portion of the application, this functionality. So it can tell you like, okay, well then don't change any of these bytes. If you change any of these, you won't get to that same location. So then you can basically, you know, filter those out and say like, okay, I can change these bytes over here and I can still get to the same place, but I'm still mutating the file.
You know, in the exploit development world or even the exploit selling business, more than once have I heard exploit developers boast about how deep their bug is that they found. And the idea behind it of saying, oh man, this is a high quality vulnerability or a high quality exploit, because it's very hard to reach with something like a fuzzer. You know, if you think about fuzzing an application with AFL, there's probably been dozens of folks that have tested popular applications which have hit surface level bugs. It doesn't mean that same mutational fuzzer couldn't trigger the same condition that's exploitable, but this type of white box fuzzing that we're talking about, or concurrent testing, can definitely get you access to deeper bugs, which, you know, just as powerful. They're just maybe more likely to find something because someone hasn't come down and really beaten all paths that, you know, that could have been executed.
Right. One thing I want to get across here is white box fuzzing or concurrent testing is not the end all be all. So there are a lot of pros to it. There are also a lot of cons. It's a very computationally expensive way to handle things. I mean, you're not going to run this on your Chromebook, right? You're going to need a big beefy computer with as many cores as possible, lots of RAM, right? You're not going to be able to run 1,000 of these a second. You're going to be able to run 1 every 2 minutes, right? It's a lot slower. But again, there's the trade-off of, you know, do I want to go get more iterations, or do I want to try and get more, I guess, do I want to get deeper, I guess is one way you could say it. So there's really kind of 2 schools of thought in fuzzing. And one is go dumb and just get as many iterations as possible. And the other is like go smart and, you know, try and replicate as much of the behavior as you can and reach more functionality. And it really kind of depends on, I guess, your resources. So like the teams at Google, they have a lot of resources behind them, right? Like I think a couple years ago, Chris Evans talked about the scale of fuzzing at Google. And he said they had something like 9,000 cores available just for fuzzing, not for anything else, but just for fuzzing. And then shortly after that, they put out a blog post saying they were going to quadruple the size of that. And, you know, this was in like 2014. So who knows what the size is now? Like, I would not be surprised to find that they had 50,000 cores fuzzing 24 hours a day, 7 days a week, right? So when you have that much resource power behind you, yeah, it's very simple to just go dumb and run 1 billion iterations. But if you don't have that kind of resources, you might want to be looking at something else like a more of a focused approach. Whereas dumb fuzzing is just very broad and we're going to try all these things. White box fuzzing is very much the opposite of that, and it's a very focused approach. So I think we've kind of beat the techniques to death. What One thing I wanted to talk about is like really why is the attacker doing this? Like why is the attacker fuzzing? Right? So we know some of the reasons, right? The attacker wants to find a crash. We talked about that a little bit. But like what are they trying to do once they get the crash? They're going to have to take that crash and they're going to have to analyze it to determine if it's an exploitable vulnerability. Some crashes aren't really controllable by the attacker, really. They're just useful for denial of service, right? If you open your browser and you go to this URL, your browser crashes. It might be useful in some cases, right? But like in that case, I'm just not going to go to that URL again, right? It's not that useful. So they got to kind of figure out like, okay, we found this bug. Is it useful?
So Chris, picking up on that, the usefulness of it, we see this a lot, right? That's where some of that code coverage that we talked about before. Crashes in a lot of ways are cheap, right? Not every crash is exploitable. I would argue, I won't say more often than not, because there's a lot of creative hackers out there who continuously proved a non-exploitable crash was indeed exploitable. But that's something I think we need to, at least bring folks back down to reality.
Yeah.
You find crashes. We found, sometimes in software, popular software, Chris mentioned DLC, you can find dozens of crashes. How many of those actually lead to something more than a DOS, where you cause the program to crash or freeze up? I'll say that's more of an art than a science to give a hard number, but that's something to be aware of.
Yeah. I mean, if you want to be proven wrong on the internet, go out there and point to a bug and say, this is not exploitable. Basically, that will immediately cause a bunch of people to go and look into it, figure out if you're wrong.
And prove you're wrong, I think.
Yeah, just never say whether or not a bug is exploitable or not. Just assume it is and move on, unless you want people to prove you wrong.
Oh, goodness. So, Chris, we want to talk about users. Every Tradecraft Tuesday episode, we make sure we highlight, hey, here's how hackers, security researchers, etc., can do this malicious functionality, but we try to caveat it with remediation recommendations or just protection.
Right. Absolutely. Yeah. Like how can you protect yourself from this? So,
Chris, so how can a software user protect themselves?
Yeah. So how can a software user protect themselves? This is kind of the this is kind of like the problem area, right? Like there's not a lot that you can do to protect yourself from this. Some of the things you can try and do are there's a software that Windows puts out. It doesn't come with Windows by default, but it's free. You can go and download it. It's called EMET, E-M-E-T, the Exploit Mitigation and something tool. I can't remember the second E. But basically what it will do is it has a bunch of filters for things that appear to be exploitation-like techniques. And whenever it detects these, it will prevent them by usually just crashing the application. So going back to the same example we've been using throughout the show is Adobe Reader. So if Adobe Reader opened a PDF and the attacker's PDF did some things and Emmet detected it, it would immediately kill Adobe Reader and the attacker wouldn't have code execution. They wouldn't be able to do anything malicious on your box. Did you forget what that second E was about?
Yeah, I actually pulled it up. We're live chatting about, laughing at it as a group. Enhanced Mitigation Experience Toolkit. But
oh man, I was way off.
I think we were close.
I was way off. Close enough.
Close enough indeed.
So that's it. So that's as an end user. Let's say you're a software developer, you're a vendor. We talked about this a little bit before. Is before you release your code, fuzz it, right? It's a one-time thing to set up some very simple mutational fuzzing. You can set it up as a job that gets spawned off of Jenkins or something like that. It's very easy to set it up, and that just it's not going to protect you. Like you're not going to find all the bugs that way, but you raise the bar from here to like up here, right? And anybody else who comes along and does the same dumb fuzzing, they're not going to find any more bugs like that because you already squashed them all before you released it. So that's what you can do. Keep yourself out of the news. Keep the bad PR to a minimum.
All right. I'm thinking of an Elsa quote here that applies to fuzzing, which is terrible, but just let it go, fella. There's no reason that your fuzzer can't just friggin' run.
Yeah.
We harp on this a lot. You will have better software by putting in a little bit of effort and just let your terrible dumb fuzzer run. I promise you'll find crashes. This is any project out there.
Right, right. I mean, if you're a development shop, you know, you're probably going to do hardware refreshes every now and then. Instead of throwing some of that hardware away, put it in the corner, let it fuzz stuff all day long, right? All right.
We address then really like as a software user or a software developer, what you can do with fuzzing. I mean, anything else you want to add as a software developer, what you could do? Or, you know, we could talk about what a security researcher could do. We kind of already did with, you know, Google's Project Zero.
Yeah, yeah. Yeah, I mean, as a security researcher, you know, this is something that you can do in your spare time, right? If your day job maybe has you doing some sort of development, but you really want to like get into this whole bug bounty thing, maybe you want to switch over to be a security researcher. This is an easy way to get started. Go out there, read some tutorials on AFL, read some tutorials on Sully, and the best way to learn it is to just do it. Go out there and do it. See what works, see what doesn't work. Maybe you'll earn some money through some bug bounties. Yeah,
run it in your sleep. We did it at the class last year where someone said, hey, could you do this to QuickTime or do this to iTunes? So we literally on the fly adapted our fuzzer, which was beating up VLC and made it beat up QuickTime and iTunes. Walked away with 4 unique crashes, uploaded those to Apple. They said thank you. The equivalent, and I won't throw the vendor under the bus at all, the equivalent was done on a different piece of software. And what's neat is by the time the vendor came around, they had a bug bounty program set up, and just with a crash, not even like here's how it's exploitable. They literally just turned over files, the fuzz files or the input that would crash the software, and folks got paid bug bounties out of them. So, you know, this is something that, you know, I don't think you could probably make a living on it, doing it without getting better. But just off your hobby, I think there's very likely, you know, that you can get yourself at least a CVE saying, hey, this is crash, this is a DOS, etc.
Right. Why not? Even if the vendor doesn't have a bug bounty program, if it's possibly exploitable, I mean, ZDI, Zero Day Initiative, they still buy bugs, you know, and they buy them for the defensive purposes. So they buy the bug, they report it to the vendor, they add a signature to their tool, Tipping Point. The idea being that any of their customers who run Tipping Point are now more secure through that means. So there are things you can do to you know, turn your hobby into a new career, or even just a little extra money on the side to have a little fun.
So Chris, we've had some questions, and I want to get to those real quick. One of them, we were talking about AFL a whole lot. Can AFL work with network traffic fuzzing? Was one of the questions.
Yeah, it's not. So AFL can really kind of do anything. You kind of have to work around it and build scripts to do it. But yeah, you can definitely do some traffic fuzzing. Some things are easier to do than others. Very simple file formats are really easy to do. Things like that. Not as easy, but if you want help or anything like that, there's actually a very helpful mailing list, the AFL mailing list. It's not too bad. So if you join that, you'll maybe get a couple of pieces of extra email a day, and you can ask questions on there, and everyone on there is really helpful, and they just want to see AFL and work and make it better. So if you get stuck, ask some questions.
So another question asked by Pronto on this one here is, are there any good training examples? Like where could someone learn to fuzz, or what could they get confirmation to fuzzing? Do you have a preference, whether that's CTF style examples, crash me's or fuzz me's equivalent?
So this is kind of something that I have recently run into that is, there just isn't a lot out there. The problem with the CTF binaries is CTF binaries are very specific, right? They were made for mostly the sole intent of having one vulnerability. Often it's not that easy to find unless you're going for one of the really easy CTFs. Similar problems with crackmes. Again, it's a very contrived example of a single vulnerability. So harder to find with fuzzing. There just really aren't a lot of good examples out there for like, oh, I want to practice fuzzing. Hopefully within the next month or so, depending on how long it takes me to get back to my regular self after Black Hat in Vegas, I'm actually gonna go ahead and release a binary that I've created for as part of the training course. And the sole purpose of this binary is it has a bunch of different vulnerabilities. Some of them are easy to fuzz, some of them require you to fuzz with different techniques. But I'm hopeful that it's a good kind of like a learning tool for, how can I fuzz and what do different techniques do. So we'll put it on here when we do it, and we'll tweet about it and stuff. I'm going to upload it to GitHub, and then hopefully anybody who's interested can download it and check it out.
I would also like to plug, I think exploit-exercises.com has the Protostar challenge on theirs. And if I recall, it's a bunch of buffer overflows, maybe some format string vulnerabilities, but the point behind it, very easy to crash binaries. Although I've never thrown a fuzzer at it before, I do recall the Protostar exercises being easy to crash that way.
Yeah.
So Chris, we're coming up. We're 43 minutes into this. It's been a solid episode. Got good questions. I guess we'll open up the floor. Here's a chance for anybody, whether you want to tweet, hit us up in the Pound Live channel and Tradecraft Tuesday Slack. You got any finishing notes while we're waiting for those questions to come in?
No, I was just checking out Slack here. If you're interested in this, there's a couple of books on it. Not all the books are equal. One of the best ones I've found is it's called Brute Force Vulnerability Discovery. It is by Michael Sutton, Adam Green, and Pedram Amini. It's from a couple of years ago. A lot of it talks about some tools that are kind of out of date, but the concepts in there are still valid. So if you can get your hands on that book or something, that's a decent one. I heard some rumors maybe about a year ago that some people were working on a new updated version of a book on fuzzing, but I haven't seen anything come out of it yet. But there's a lot of tutorials online for really how to get started with Sully or AFL. So if you're interested in learning more, go check those out. Shameful plug, we teach a course on it. Which
Shameful indeed.
Obviously I'm biased, but I think it's like the best one.
Somebody mentioned, and I skipped over the question earlier, but Vermin pointed out libfuzz for LLVM. I believe the point behind it is coverage-guided fuzz testing. That's at least what the page says. Know anything about it, Chris?
I have heard about it. It doesn't appear to be all that popular. Something else that's pretty popular is we didn't really touch on. It's more of like a technical thing. It's called Address Sanitizer. So Address Sanitizer is a plugin to LLVM where when you compile your code, it will add in a bunch of stuff so that you end up with a bunch of runtime checks. So whenever the target application allocates memory, Address Sanitizer makes a note of that. Whenever your target application frees memory, Address Sanitizer takes a note of that. And any accesses to memory, Address Sanitizer can then say, okay, this is an access that is valid because it's within an allocated buffer. So it can find things like if you found a heap overflow and you wrote past the end of the buffer, Address Sanitizer can find that very easily. It can find use after freeze. It's very popular for Chrome. For one of the major bug classes in Chrome is use after freeze. So people will build Chrome with Address Sanitizer enabled, and then immediately as soon as some memory that was previously freed is written to, Address Sanitizer will crash the application, and then you'll know right where it happened, what happened. It has some really good information. Like it can tell you, okay, this buffer of size whatever was allocated here, and it was freed here, and then you reused it here. So that's a really popular tool. Unfortunately, Address Sanitizer can't really be used with AFL unless you're fuzzing 32-bit binaries, and there's some other caveats, but hit me up on Twitter if you're curious about some of that stuff.
And Chris, that was a really good thing to mention there. What you just covered for folks that didn't notice it. That was a style of instrumentation that's not solely based on a program crashing, right? That's real. Sometimes you're able to influence a program and make changes to a program that don't result in the crash, or maybe the exception is properly handled. So when you get into more advanced fuzzing, that's something that could be useful, using address sanitizer for that purpose.
Yep.
Alrighty.
Any other questions?
I think we've hit it. I'm going to go check Twitter one last time to make sure we didn't neglect anybody. But it's I think today was a pretty solid episode, Chris. So thank you guys for kind of giving us the heads up of, hey, you're teaching a class. Why not talk about it? I don't know why we didn't do this before, actually. We do hope anybody who's watching this before Black Hat or DEF CON, we'd love to see you on Thursday night. Please take a look at our Twitter account. It's at Tradecraft2s for the updates on when we're getting together for that dinner. Once again, if you like any topics, you just have to ask. I think we've got 3 or 4 lined up over the next couple months that are based on user feedback, so it really does work, and we really do listen.
Yep. Yeah, thanks for coming out. We hope to see you again next week.
Awesome. All right, guys. Have a great one.
Yep. Later.